An element library in XPS serves two functions. One is to identify peaks within an XPS spectrum, and the other is to assist the quantification by XPS. Quantification requires peak areas to be calculated, and then these peak areas are scaled by what is referred to as a total sensitivity factor. And this total sensitivity factor is the product of the transmission response for an instrument, which varies as a function of kinetic energy, the escape depth that relates to the inelastic scattering of electrons that varies as a function of kinetic energy, the cross-section that is related to the probability of a photon of a given energy ionizing an atom, and then finally there's an angular distribution correction that relates to the relationship between the X-rays as they arrive at the sample and the direction sampling the electrons leaving the material. And so that relates to the angle between the X-ray source and the analyzer. And once all of these have been combined together, we end up with this total sensitivity factor that can be introduced into an atomic concentration calculation that relates the areas by dividing by these sensitivity factors to the total signal that is obtained by summing all of the areas involved in the calculation, all scaled by these sensitivity factors. An element library tabulates for each photoemission peak a sensitivity factor or a relative sensitivity factor, and in the case of Schofield sensitivity factors, the library simply contains the cross-section. And then we have to calculate the transmission function, the escape depth, and the angular distribution correction in order to perform this calculation of atomic concentration. There is an alternative to using Schofield cross-sections, and that is to provide sensitivity factors that are empirically determined from standard materials. If you know the transmission function, and you know the angle for the X-ray source to the analyzer for the instrument that measured the standard materials, then you can remove these from these sensitivity factors. But in general, empirical sensitivity factors will include the escape depth correction and the photoionization cross-section that corresponds to the Schofield cross-section in a Schofield-based library. This means we have the potential for tabulating relative sensitivity factors that depend on the X-ray anode material, so aluminium or magnesium. And we also need to allow for the fact that different instruments may tabulate different forms for sensitivity factors. And the way this is performed in CasaXPS is to produce an element library that includes information about the anode and the sensitivity factors that go along with the anode. So these are just Schofield cross-sections that correspond to an aluminium anode with a given X-ray of 1486.6 eV. And also within the same library there's an entry for magnesium anode materials, so this is a photon energy of 1253.6, and the RSFs are different for each one of these photoemission lines based on an aluminium versus a magnesium anode. And then there's another alternative where a specific instrument is indicated by a source label that is different from aluminium and different from magnesium. So this is an example of a K-alpha entry, and we also have an entry for a phi instrument, and again the phi instruments typically use an aluminium anode, so these are labeled phi 1486. This is relating to the photon energy, but this indicates that these RSFs can be tabulated as distinct from the aluminium magnesium Schofield library, and these will be offered for any data for which the VAMAS field within the VAMAS file for the spectrum states phi 1486 as opposed to aluminium. When a VAMAS file is created by CasaXPS, it's possible to configure the source label that is entered into the VAMAS blocks. So in the CasaXPS directory that contains the default files, that's casaxps.def, there's a file that is called parameterfile.txt, and parameterfile.txt includes an option where you can enter phi source label should be turned off, in which case the default will be AL for the source label, or you could change it to say phi source label, in which case when a file is converted, then the VAMAS block will contain a source label that says phi 1486 to match the element library. With a phi source label in the configuration file, at the point that a file is created, Convert to VAMAS file dialog window, selecting an SPE multipack file and then pressing the open button converts the data within that file, and the source label is then phi 1486. So when the element library is selected, the lines that are displayed in the element library correspond to the lines that match the source label phi 1486, because these values here match the value for the source label, which can also be seen if you look at the block info. And here is the source label, and that's the energy and various other parameters that have been brought in, such as the resolution from the original SPE file. So at this point we have data that recognize the fact that they have an angular distribution correction that needs to be performed for an angle of 45 degrees. There's a transmission function that is active, and that was brought in from the SPE file, and the escape depth correction currently is set to none, and this is because if these were phi sensitivity factors, the escape depth would already be included in the sensitivity factors that are supplied by phi.